So in the last video, when we calculated the angle of diffraction for the setup, we saw that the angle of diffraction was about 0.14 degrees. And for a lot of experiments, you'll find the diffraction angle is quite small depending on what you're looking at. And things that are really small are going to be hard to measure. So sometimes you want to see if we can find a way to work around that. So what we're going to look at is this thing called the small angle approximation. Now, what we're going to be looking at if we're looking at our experiment, we have a few distances again. So there's still that distance between the slit D, but the new ones that we're going to introduce, and this is one of the complexities of Young's experiment in Physics 30, is there's a lot of different distances we're looking at, so you have to know to distinguish between them. So the distance between the slits and the screen, this is what we're going to call L, and the distance between the central maximum and that fringe that we happen to be looking at, we're going to call that distance X. What you'll notice is that my angle of diffraction, that distance between the slits and the screen, L, and that distance between the central antinode and the fringe that we're looking at, these form a right triangle, but specifically this angle is going to be related to L and X through the tangent function. So we know that tangent of theta is going to be my antinodal distance, or that distance between the node. Oh my goodness. It's going to be that distance between the fringe we're looking at in the central antinode over that distance between the slits and the screen. So we know this relationship. This is useful to know. I'm going to also put this. Use this to check angle. Sometimes in an experiment, or in a question, and I'm going to talk about this later, we're going to ask you to check the angle of diffraction because you want to be able to see if this approximation we're going to show you is valid. So we want to use that relationship between x and L and that tangent function. Now, tangent theta equals x over L is nice. The problem is the equations that we learned to look at diffraction and wavelength and slits and all that, it has sine. Sine and tangent aren't the same thing. This is where we're going to put in our little approximation, our little trick. What we find is that for angles that are quite small, and we're going to say for us, we're going to restrict small to about theta less than 10 degrees, what we're going to find is that the tangent of that angle, it's pretty close to sine of theta, like it's almost indistinguishable. So what we can say is that for angles that are really small, we could say that tangent theta is roughly similar to sine theta, under this restriction though. So instead of saying tangent theta is equal to x over L, well, we could say for small angles, sine of theta is roughly equal to x over L. This is helpful now because in our diffraction equations, we've had sine of theta. So where we have sine of theta, we have x over L. But just if you have to check the angle, you're not using sine theta equals x over L, you're using the actual relationship, this tangent of theta equals x over L. So something to be aware of. Now, what that allows us to do in our equations for constructive and destructive interference, that allows us to actually get rid of, well, sine theta. So where we had a sine of theta, we're going to get rid of that for x over L. So we could say that lambda is equal to xd over nl for constructive interference, and then for destructive interference, we could say lambda is equal to xd over n minus 1/2 L. So lambda is going to be our wavelength of light. X is going to be that distance between the central maximum and the fringe that we're looking at. D is the distance between the two slits. N is the fringe order. And L is that distance from the slits to the screens. Now, the small angle approximation is really great, but it's one of those things on the diploma they'll try to bait you into using when it's not actually appropriate. So these above equations, they're only valid when the angle is under 10 degrees. If the angle is larger than 10 degrees, you need to use the actual lambda equals d sine theta over n. You want to check the angle before you use this. Now, the other thing is, you'll notice even for angles less than 10 degrees, if you're kind of getting close to 10 degrees, 8, 9 degrees, you'll notice this equation and lambda equals d sine theta over n, they'll start to give slightly different answers. What that means is our two models, they're starting to diverge from one another, and the accuracy between the similarities between the two are starting to decrease. Keep in mind that lambda equals xd over nl and lambda equals d sine theta over n, they are built on assumptions, so neither one of them is like 100% accurate. Lambda equals d sine theta uses the whole idea that the screen's infinitely far away to make that right triangle to allow us to get that sine function in there. but that's not 100% valid. These equations here, they're still assuming that screen's far away, but they're also assuming that the angle is small enough that we can say that sine of theta is rough and tangent of theta are indistinguishable. That is also a huge assumption. So both of these equations that we've looked at for diffraction, they have their limitations. So they're not going to give us 100% accurate answers, but broad strokes, it should give us a good enough answer. But make sure you check your angle. So let's look at a question with this. So we have an experiment. A student is going to use monochromatic light. So if you see the word monochromatic, don't let it scare you. It just means one wavelength. And in this case, this monochromatic light has a wavelength of 550 nanometers. So using a double slit apparatus, the spacing between the slits is 2.50 times 10 to the minus 6 meters, and the distance between the slits and the screen is 0.0750 meters. We want to determine the distance between the central maximum and the first order bright fringe. Now, with all these diffraction questions having like many different distances, let's actually kind of set this up, or let's write our variable list. So we know our wavelength is 550 nanometers, or 5.50 times 10 to the minus 7 meters. We are told the slit spacing D is 2.50 times 10 to the minus 6 meters. We're told the distance between the slits and the screen is 0.0750 meters. And we want to find this x value for the first order bright fringe. Now, we have lambda, d, l, n, and x. What this is trying to do is this is trying to bait you into using lambda equals xd over nl. We better check this though. Let's check the actual, we want to check the angle. But the problem that we're actually having right now is we can't check the angle using tangent theta equals x over L. We don't know x. However, we can use our original diffraction equation. So to check that angle, we know that lambda equals d sine theta over n. We know that sine of theta is n lambda over d, or theta is just the inverse sine of n lambda over d. Let's see what that angle comes out to be. So we get the inverse sine. We're looking at the first order fringe. We have our wavelength of 550 nanometers. And we have that distance between the slits of about 2.50 times 10 to the minus 6 meters. And we're going to get an angle of about 12.7 degrees. And this is why I've picked this example. If we just use lambda equals xd over nl, that assumes the angle is under 10 degrees. The angle is actually not under 10 degrees. It would be wrong of us to use that equation. So we can't use that. We have to use this formal method. So now that we know lambda, so now that we know the angle is 12.7 degrees, now we can use the relationship of tangent theta is equal to x over L. This doesn't assume small angle. This is always going to be true. So x in this case is going to be this distance between the screen and the slits times tangent of our angle. And again, that angle is going to go here. So that's x. This is going to be the length of our slits, or the distance between the slits and the screen. So we've got that 0.0750 meters times tangent that 12.7 degrees. And then for this, we are going to get about 0.0169 meters, or we could say 1.69 centimeters. So that's what we're going to get. We had to use the long way to do it. So you might ask, why are you using this, doing this in the small angle approximation? Again, we're just trying to show you how they try to bait you into using the small angle equation when it's actually not proper to do so. So I'm just going to show down here if we use the small angle approximation. Obviously this is not something you would be writing down because it's not correct to use this. But we know lambda is equal to xd over nl. So x is going to be lambda nl over d. So if I calculated that based on this equation, what will we get? So I'm going to run out of space here. So I'm just trying to cram this in as best as possible. So if I do it this way, what am I going to get for x? So I'm actually going to get about 0.0165 meters. Now you might say that's not a lot of a difference, but keep in mind, as we start to increase that angle, this difference is only going to get larger. So, but at the end of the day, if you always want to at least be like sure, or sorry, let me phrase this. If you at least want to be like confident that your answer is, you know, the better of the answers, use lambda equals d sine theta over n. That is the more general equation. But watch out for the small angle approximation. It's really convenient, but you can only use it if the angle is small. And beware of those questions where they'll try to entice you to use it, but it's not actually appropriate to do so.